Hi, I'm Ned, and I've started streaming. This is a recording from my live stream over on twitch.tv/NedMakesGames. I'm live most Mondays, Wednesdays, and Fridays at 10 a.m. US Eastern Time. I'd love to see you there. Okay, hey everybody. Hope you've all had a great weekend. Mine was pretty good. Yeah, just actually I was pretty busy, but it was still a nice weekend. But let's just jump into game development. So I've been working on these tessellation showcases for the last couple streams, mostly because I'm preparing a tessellation tutorial video. And if you don't know what tessellation is, basically you can use a shader to add extra triangles to your mesh to give it more detail. And so here you can see this shader adds a line for every actual line on the mesh. So you can see as you get closer, it dynamically adds more edges, and you can also notice that the silhouette of the sphere becomes more round as you add more edges. So that's one cool thing you can do with tessellation. Let's see here. I also have set up this sword showcase, and where is it? So here I have on some tessellation, so you can notice it's smooth, and then here it's still, I managed to get it sharp, but then you can turn off the tessellation smoothing, and here you can kind of see, well, it's a little easier if you can see back to back, but you can see that the mesh is not quite as smooth. If I turned off the normal map, it would be a little bit more obvious probably, but why would you do that? Anyway, so yeah, tessellation, that's one cool thing about it. You can also make these height maps with tessellation, which I've been working on a bit lately. This is all controlled by a height map texture. And so I can lower the altitude, and you can see the mesh changes, and it all happens inside the shader. Doesn't work quite very well with negative altitudes, but yeah, people that have been to the stream know that I've been kind of struggling getting the normal map to work. I think I was just coming from it from a bad, I guess I was overcomplicating things. Because you can see when the normal strength is really high, you get like these kind of Minecrafty step things. So one way you can fix that is just to lower the normal strength. It's never going to be perfect, just because basically we're kind of generating our own normal map at runtime, but obviously if you just use the actual normal map, you'll have higher quality normals, mostly because they can kind of smooth out those edges, and it works better with mip maps. But anyway, I do need to come back to this, but for now I think we're gonna start on a new showcase. I want to make like a deformable wall. A folder. And basically this texture or this wall will try to get out of the way of a ball that we can move around. And I want to basically only tessellate areas that are actually going to be deformed. At least that's my idea. Looking for, oh yeah, new scene. So we'll get started by creating a plane. Let's rotate it guess it can stay like that, and then we'll have the sphere, and so wherever we move the sphere towards, it will deform the plane. It'll mostly happen on the GPU in a shader, but we'll have to have something that will, I don't know, output the position of the sphere, but we can deal with that later. Okay, so I want to add a couple shaders, and I guess I'll start with our existing tessellated shader, and we can just modify it. I think that'll be the easiest. So okay, so we created the shader files. All right, so I'm not sure exactly how I want this to look. I think I might, you know what? I think it might look best actually if it's a wireframe so we can really see what's happening. Yeah, so maybe, okay, we'll actually start from the wireframe shader, but okay. And yeah, we'll come back and add more stuff as we need it. Okay, so yeah, I just need to change this to read from the right file. Okay, and I'll copy all of this. Okay, so change this include line just to be best practices, I guess. Okay. So I think we'll still only need the position and the normal for all this. The geometry function is just for the wireframe part. So I think the interesting part will happen here because we'll have like a list of deformers. I don't know how many. Let's see. I guess just one for now, actually. Okay, and then we'll also want to have an integer for the deformer count. This will just be the number that's currently in the scene. Okay, you know what? Actually, I'm going to make this a float 4 because we'll have the position and then the fourth component will be like the size of this or the radius of the circle. Okay. So what we'll want to do, first of all, I guess let's do the deformation first and then we can do the dynamic tessellation. So what we need to do basically is in the domain function, we need to offset this position along the direction opposite the deformer. So this, okay, so this normal will actually be different. Yeah, it'll be interesting to calculate the correct normal. That's something we'll have to think about. Because yeah, we don't actually know our immediate neighbors, but we know the 3 points of the original triangle that we were tessellated. So I guess what we could do to get kind of close normals is we would maybe deform the normals in the patch constant function, and then we could interpolate them. I don't know. We'll see. Okay, well, I guess that with that in mind, let's just make a function that will take of world position and then return like a deformed position. So this will be the position in world space, and then we'll have this float for, oh no, let's do this. Deformer, and then we'll have the float deformer radius. Okay, so I guess this should be the vertex position. Okay, so we want the direction pointing from the deformer to the vertex because that's the direction that we're going to move away from. And then you can normalize that. I guess we actually just want the difference because we're going to have to find the length as well. So what do I want to call it? I guess deform, I don't know, difference. I guess that's fine. Oh yeah, that should be a float 3. And then the deform direction. Okay, so that's the same as normalizing it. So I guess what we do, let's just see how this looks. So we want to see if this length is shorter than the radius, then we will basically meet this. But if it's longer than the radius, then we don't do anything. So I guess the deform length then is, okay, so if the distance is, I guess this is the maximum, right? Oh no, we want the minimum of that. Okay, so length minus deformer radius. And then I guess, okay, so let's just see how this looks. I don't think this is going to be correct, but okay. And then we'll just change the position. Okay, actually, yeah, so if we have multiple deformers, how do we, I guess we would want, that's an interesting problem. So actually, another thing is that this probably should only be deformed. Okay, well, let's not worry about it. Because, yeah, if we have multiple ones, we're going to have to figure out how to combine deformations. And probably it should only be offset like normal in the same direction as this surface is normal. Yeah. But anyway. Just do it like that for now. Oh, you don't need the equals or the semicolon in it. Define. Implicit truncation. Huh? Oh. This should just be. That's not related to what we're doing right now. Oh, yeah. And don't need to subtract there. Okay, so now we need a C# script that will basically upload this sphere to that array. I think I'll put it in a separate file or a separate objects. That way, if we have multiple, we can just attach them all to the script. Okay, so deformer. I guess I'll just call it the manager. Okay, so what I want to do here is have a list of every object that might deform this wall. Okay, so actually, yeah, we need to also assign a radius. Okay, so let's make another script that's just for like the actual deformer itself, and it'll basically only hold that a radius value. I really need to fix my Visual Studio integration with Unity so I can get back some good templates. I don't know, they disappeared one time when I had to reinstall Windows. I just haven't had a chance to fix it yet. Okay, and then on update, we'll basically check the position of each of these and rebuild the deformer array and upload it to the shader. guess I need private vector for shader buffer. Oh, this should be an array. And then on start, we'll create this. Okay, and then here on update, first I guess we'll clear all the shader buffers. Or clear the shader buffer. All right, and then so we need to go through and find the number of deformers that are actually active. So if deformer dot, okay, that's fine. Okay, so this is the shader dot set global integer. All right, so let's look here so I get the name correctly. Right, and now we can also okay, so I can just do this at the same time. So shader buffer num active equals new vector 4. Let's do this. Position equals deformer dot position or transform position. So the XYZ are the position XYZ. And then the last one is the deformer radius. Okay, so we built those at the same time. And now we can set global vector array. Okay, so that should be all I have to do here. So now I just need to add a deformer object or component to this. Okay, I think I'll just remove the colliders because they're not actually going to do anything here. Let's give it a radius of, okay, let's make it fairly large right now so it's obvious what's going on. Okay, max deformers is 1. Oh, that's one other thing I need to do. So yeah, if num active is greater than or equal to the max deformers, then we need to break at this point. I guess technically this should go first because, I don't know, if for some reason max deformers was 0, then you'd have to break early. Okay, so now I need to create a material for the deformable wall. So let's place it on there, and we'll just make the wireframe, I don't know, yellow. Why is it not coloring anything? Okay, I don't want to set up all the materials, so I think I'll just copy the settings from here and then just rename the material. I'm not sure why it's showing up so dark. Oh, it's just because the light's not shining on it. Okay. How is this? Well, I don't know. It doesn't really matter. In game, I can't actually see anything because it's not facing the camera. So there's probably a better way that we could arrange this. So, where's the camera? Oh, it's over here. Okay, it's not gonna play nice with me. There we go. Okay, now why is it sticking to the grid? Did I just wanted to turn off the grid. Okay, there we go. So let's stick the game view down there. Okay, so it's not deforming at all, but it's definitely getting a really big shadow. Okay, so the deform, the radius actually affects that shadow, so something is happening, but I don't see any deformation. Okay, let's see, look at the shader. Oh, it's because I need to do it here. The way I've organized the code is a little confusing. So float through, so I should, yeah, the position. World space equals. So the reason was because the world space position was being changed, but since here when we transform to the clip position, which is what the position the GPU actually uses to draw things, it was using this variable, which we were only updating the variable on the output structure. Okay, so now should be. Okay, so it is working, but yeah, like I said, I didn't think it would actually work how I wanted because you can see it's moving away from the sphere in all directions when I kind of just wanted to move normal to the wall. So what we can do to fix that is do like a projection. Okay, so I'm trying to think, when we have multiple balls, what we'll want to do is basically find the longest deformation and use that. So in order to do that, we need to return just a distance instead of a vector. So probably, I guess we'll still use this. We'll still need to have this normal, but we should just return the length of the projected vector and not the actual vector. So let's change this. So deformation length. Okay, I'll change this to movement, direction. Okay, so we have to get a project function, which I think I might already have one. It doesn't include, it's not included in HLSL, but I think I had to do it in one of my tessellation effects. Let me see. Well, this is basically it, but let's just look up. Okay, that's not what we don't want to project to a plane. We want to just project. Okay, yeah, well. I was hoping I'd just get it in programming so I don't have to translate from math notation, but that's okay. The purpose of the section is to show how to compute the projection of vector u onto v. Blah, blah, blah. So yeah, it's projection of v dot u over the length of v times v. So if I want just the length of the projection, I don't have to do that final multiplication. Okay, so just to make sure we're projecting u onto v. So, okay. Float. V, and then I guess it's float 3. And then float 3 axis. So yeah, we'll project v onto the axis. Okay. I'm kind of doing it opposite there, but it's fine. So it would be axis dot v over the length of axis, which, okay, well that's really easy because since the normal is always a unit vector, then basically it's just a dot product. So I actually don't even need this. Okay, so that makes things nice. Okay, so what do I... Okay, so float 3 formation offset is that, and then I could just return deformation offset, or the dot product of deformation offset times the normal vector, or the movement direction. Right, and then, okay, so we gotta switch this up a little bit. That's the num deformations. Probably would even be faster if, yeah, so if the radius is 0, then that means nothing will change. So probably, because of the weird way that shaders work, it'd be faster if we didn't even use this deformer count and we just always looped through the maximum number of deformers. And then we just made sure that the radius was 0 on any that weren't active. Which actually, that is kind of how the C# script works. The reason that's nice is because it makes this loop, we can unroll the loop, which means the compiler will basically just remove the loop and copy this code multiple times. And that is good because it lets you not have to have a branch in your shader code, which can sometimes be kind of slow. So I don't know, maybe I'm prematurely optimizing here, but it seems like it might be nice. Okay, so max deform length 0, and then we'll just set max deform length equals or this. Except I rename the function. And this should be I now. Okay, and then position world space, we add the max deform length times the normal vector. Okay, so let's see if this works a little better. We got an error, undeclared. Okay, so first we got a truncation again. Oh. Just think that hasn't updated yet. I don't know why it's still showing me that. Implicit truncation of vector type. So float 2 for UV. Then I'm already doing .r. Did I? Okay, I don't know why it's telling me that there's a truncation there, but okay, it hasn't updated yet. Okay, undeclared identifier max deform. Oh, I just spelled it wrong. Okay, so if we move this close to the wall, okay, nothing happens. Okay, so changing the radius doesn't do anything. So yeah, it's just not deforming. Let's see, what would be a good way to test this? I think it'd be nice if we just output this deform length as a color. So let's just add another. Okay, so we've got, it has to go through the geometry and the interpolator, which is sort of annoying, but okay, so deform color, and we can, I don't know, we could maybe use this for an effect as well. Well, actually, I mean, we could kind of stick it onto the end of the world space, so I don't have to have a new text chord. I mean, why not? Okay, so output float 4. And I don't think I have to update anything else really, except whenever I use the world space position, I should use XYZ. But let's do this. So position, world space equals input, position, world space dot XYZ. I guess let's just see where this is used. Okay, so quite a bit. Oh, but I didn't actually do anything. So I want to just output the deformation for now. So input, position, world space. Okay, yeah, so it's saying that there's no deformation. Making sure I'm not making a silly mistake. Okay, so first we find the difference in the positions, and then from that we get the length and the deformed direction. And then we take the minimum of the length and the radius. Then we multiply that with the deformed direction to get like a ideal offset, and then we project it so it's always parallel to this movement direction by taking the dot product of them. Which we can do it that way because we just want this part, so we don't need to do that, but then also the movement axis is always normalized, so we don't have to take the length, so it's just the dot product. So I think, I mean, that all looks right to me, but obviously something is wrong. Okay, maybe we can let's just do something silly here just to see what happens. We'll just return the length of the position vector. Okay, so I mean it does deform at least, which is good to know. Okay, so something has to be wrong with this math. I guess the other thing is that, oh, you know what? I think it has to be in play mode. Is that why? Yeah, because the script doesn't update when it's not in play mode. Okay. No. When I move past it, it doesn't happen when I'm on the other side. Okay, yeah, it's like inverted right now. Because you can see the farther I move away on the negative side, the more it's moving. Okay, so it kind of works here, but it's like the opposite of what I think. All right, so what's happening here? So the difference, so here so it's the target minus the start. So if we start here, okay, so this is giving us the direction from the deformer to the vertex. So yeah, that's the direction I want it to move, right? But maybe I can try inverting it just to see. I don't know. Okay, yeah, so now it was the direction from the surface to the deformer, which doesn't do anything. Oh, well, of course it does nothing because it's not in play mode again. So okay, that's not right either. Okay, so maybe this is the problem. Let's just take this off. Because the thing is, okay. Why does it not work? Like, it should be that symmetric, I feel like, but it only works on one side. I thought that was because of the minimum. Oh, it's probably because we take the max here, so it deletes like negative deformations. How do I handle that? I guess we kind of want the most extreme. I guess the other option is we could just add them together, but that would not work. Okay, well, you know what? I'm not I'm not really trying to make like the perfect thing, so maybe we just go with one side. Um, okay, so I want it to go on the other side, so probably I can flip it by changing the normal. So if I go to the plane and just scale it by -1, it's gonna scale in world space though, isn't it? No, that didn't do anything. Okay, so I need to do this, but now it's invisible. Okay, so I guess we could just, yeah, it doesn't have to be perfect because I mean, basically just for demonstration. Okay, so now it follows the circle. So now if I add back in the minimum, wait, shouldn't it? Okay, well, you know what I need to do actually. Okay, so I need to just do the minimum here because yeah, the normal faces outward from the wall, but the wall is always going to move opposite its normal. Yeah, so that, okay, so I need to do the minimum. This is kind of confusing. I could just like invert everything. Okay. Maybe that would be a little bit more obvious. So we multiply by the negative normal because that's the deform direction. Let's see here. Okay, so now we're back to taking maximum. Okay, let's see. Oh yeah, this makes sense because now, okay, well it's still not correct because as we move the ball away, it deforms less. I mean, it reforms more as we move away, but I actually wanted to deform when it gets close to the wall. But I guess we're kind of getting there. Okay. Right, so let's add this back in. Now at least has like a maximum radius. Okay, so basically this is the distance from the center of the deformation ball to the vertex. So what we want to do, yeah, we don't need to deform until the ball gets like, or until the vertex is like inside the ball, and then we need to deform outwards. So what I would do, um, trying to think about the math. So basically, this length is less than this radius, and we need to bring it out to the radius. So that, do I just make this maximum? But I feel like that would mean it will always deform. Okay, so I think I need to do like a percentage thing here because if it's maximum, then this deform length will usually be more. So let's see. If deform length is less than the radius, then the deformer is intersecting with this vertex. So the vertex needs to move away. See, so okay, let's I should rename this because it doesn't really make sense. This isn't the length we want to deform. This is the difference. So let's call this difference, and then this will be the I don't know, distance deformer. Okay. Okay, so then I guess here we would take, it needs to be the radius minus the distance, maybe. Let's see here. So if it's like at the maximum distance, so the radius. Okay, so maybe I think I might be making this a little bit too difficult. It doesn't have to like totally hug the sphere. I basically just want to make it so that when I get close to it, the wall moves away, kind of like it's a magnet. Yeah, I think I've gone a little bit too much with this. So maybe instead of this being like a radius, this will be a strength. And then we'll just like increase the strength based on the distance here. And then we can still do this dot product though. Okay, yeah, I think I went a bit overboard there. But this should work. So, okay, and then it will move along there. I think, yeah, we can either do max or add. We'll have to see what looks the best. Yeah, what am I doing here? Okay. Okay, so that's not right. Deformation offset equals the deformed direction times the distance to the deformer. Okay, so again, this is increasing as the distance increases. So I actually want it to be as it's smaller. So I kind of need to have like a maximum radius, don't I? I guess I could do like 1 divided by the distance to the deformer. Obviously, if the distance is 0, then we'll get divide by 0 problems, but oh, the radius or the power is 0. I guess I should rename that. Okay, so since I'm doing 1 minus, it's going to be very strong. I also kind of want it, if I keep pushing it inwards, that I'll keep deforming. Okay, so basically if the dot product is of the, let's see here. So the dot product of the deformed direction and then the movement direction are positive, then it should continue moving. Okay. Trying to think how I want this function to work. I think I kind of, do I need to have like a maximum radius? I didn't really want to do that because I kind of wanted the maximum radius just to be defined by the deformer strength, but it needs to start at 0 somewhere. And I don't really want it to have this reciprocal because then it's kind of too strong. I don't know. I'm spending too much time on this math part, but yeah, the real meat of this is supposed to be the tessellation section, but okay, let's see. I'll just hard code in some values for now, I guess. So if so again, we need to do slightly different math depending on what side of the wall we're on. I guess this strength could just be the maximum radius, kind of like how we were doing it before. Okay, so let's see here. So if dot, so I don't know what to call this. Let's be the dot of the movement direction and then also the deformed direction. And we can tell if this is positive, then the deformed position is on the other side of the wall. So basically it'll be like just keep getting stronger as it moves by. But if it's on the negative side, then it will get weaker as it moves farther. We need to do an okay. I feel like I don't really want to spend so much time on this math part, but maybe it's just because I've already been working for a long time, but it's not popping into my head right away. Okay, so yeah, again, if this is negative, then we want to taper off as it gets closer. So, okay, so I know what I should do. Into float deform power equals interpolate. Okay, so at the maximum distance, if we use this deformer strength as like the maximum radius, then if the deform dot there's an easier way. Okay, so maybe I'm thinking, is this deformer strength will be like the amount of deformation that happens when the sphere is at 0. So if that's the case, then it would be something like I guess I could actually just use this. Oh, no. Okay, so I guess I will just do an if. Probably a cleaner way to do this. But anyway, so if it's less than 0, then we want to do okay, so if it's less than 0, then it will be basically the distance. We'll take the maximum. So 0 times the distance to the deformer divided by the deformer strength. Okay, and then it needs to, so this will be between 0 and 1. And then it needs to also equal deformer strength at 0, so I have to multiply this. Oh, it doesn't need that parentheses. Okay, so otherwise, when it's positive, it starts at deformer strength and then increases. Plus distance to deformer. I don't really like that, but we'll go with it for now. Okay. Yeah, then we don't have to do a lot of stuff. Oh yeah, there's no math in HLSL. Okay, well, that's not a good start. Oh, but it's not in play mode, so. Okay, so what did I mess up? Maybe, okay, so the normal is pointing away, but the... Well, this is gonna be confusing, but I'm gonna try that and see what happens. No. Okay, I'm just gonna do something simple and we'll come back to this because I'm tired of messing with the math. Okay, so I'm just gonna make it just be the distance to the deformer times this deformer strength. Oh wait, this is the same problem. Okay, so I'm gonna hard code in a radius. Okay, well there we go. So now we've got something. It's not really what I want. And I don't know why it's flat at that when it gets to a certain distance. Oh, because when the distance is greater than 5, it doesn't do anything. Actually, this is like remarkably good. Okay, maybe instead of saturating it, I can just do maximum. Okay. Yeah, this basically does what I want. Although, yeah, so ideally when you move through, I'd want it to keep on pushing for outwards, but anyway, this is, I was kind of trying to avoid setting another, because like I'd really like to define this deformer strength, or have the deformer strength define the radius, but I guess, I mean, it kind of does, but anyway. This is fine. So we'll start here and we can, I don't know, we'll find this function. Yeah, it's not really the point of the tutorial, so I didn't really want to spend so long on it, but it is what it is. So anyway, now that we have this deformation length, okay, so we've handled actually deforming it. So the fun part is I wanted to increase the amount of tessellation based on how much deformation that point is getting. So we need to calculate the deformation here and then basically multiply it with this tessellation factor. Or let's see. Okay, well, that's kind of confusing because the tessellation factor, sometimes the smaller ones and smaller values increase tessellation, sometimes larger values. So maybe what I should do is just let you be able to interpolate between it depending on what mode you're using. Anyway, so I need to basically average the deformation length of the 3 triangles in this patch. So float deformation equals, okay. Yes, I need to do this loop actually. So I think I can just do that. So float 3 position. And if I do that, it should, I think it's smart enough to have overloads. I forget if HLSL does or not. Guess we'll find out. Oh yeah, well. Okay, I thought it supported it. So I need to call this. So patch 0.position 0.normal. And then we'll divide it by 3 to take the average. Okay. So for now, I'll just multiply it. Okay, yeah, but you can see it's doing the opposite because right now I have it set to increase as you get closer to the tessellation surface. So yeah, I can change that to just be constant. Okay, and then tessellation factor will set to 1. Okay, so it is working, but it's not very strong. So if I go here, okay, well, actually I guess I'm gonna need to add some more variables because I want to basically have the deformation affect it more than it is. And really, actually, things that are deformed more don't really need more. It's just if something is deformed like past a certain amount, then it needs to have one value. Otherwise, it needs to have another one. So let's see, probably. Let's clean this up. Okay, so we have tessellation factor. Change this to undeformed tessellation factor, and then we'll have deformed. Or maybe we'll just put them both in the same variable just to kind of keep things slightly cleaner. And then probably like and then we'll want like a smoothing or something. This will be like a length or a range between tessellation or deformation offsets where we'll kind of interpolate between these values. So if it's when it gets up to, I don't know, quarter of a unit deformed, we'll use the entire tessellation factor. Right? Okay, so float factor equals lerp. That's fine, but I wanted the other one. I guess this was actually the smooth step. Well, okay, so first we'll interpolate between the two and then we'll smooth step. Okay, I just want to have that for later. Okay, so yeah, it's tessellating all the areas that are being deformed, and then it kind of, you can see up at the top, it smoothly interpolates a bit. It's still, tessellation is, it's still not tessellating very much though, so let's increase this something higher. Okay, so these triangles, there's a problem here. You can see there's edges, and it's because these triangles are having a different amount of tessellation than their neighbors. That's kind of why I had the smoothing, because I was hoping that wouldn't happen. That kind of fixes it, but it defeats the purpose. I think what's happening, let's see if I, okay, no, we still have, maybe is there a bug somewhere else? Because I feel like, let's see here. Probably what I want to do, well, first off, I forgot to rename this, so maybe instead of taking the average, I should take the maximum. All right, this is going to be a bit messy, but it's kind of hard to see because of the way the color is working. Just so that's not completely black, I'll just add a little bit. Okay, so now we can see that a triangle that has any tessellation is getting fully tessellated, which is probably for the best. So I guess in that case, I don't really need the smoothing, do I? Does it actually add anything? Okay, no, when I do it, it just makes... Yeah, so the problem is that any edges need to have the same amount of tessellation, otherwise they get those holes when you combine it with deformation. So... And yeah, it's fine, because we can kind of assume that anywhere without tessellation, yeah, so normally when you don't smooth stuff, you can kind of tell because it snaps, but I think in this case, since we're not using tessellation otherwise, it'll just be flat, so you won't be able to tell that there's any tessellation going on, or that there's no tessellation going on. Okay, so yeah, let's get rid of this smoothing, because I don't think it's actually going to help with anything. Okay, and yeah, so we take maximums. All right, let's see. How do I I need to clean this up now. It's confusing. I can do this a little bit cleaner using a 4 loop, can't I? Okay, so then okay, and then we can just yeah, so if the deform length is greater than 0, then we choose 1. Okay, so I'm not going to try to do fancy stuff here, because technically you could try to do interpolations and it might be faster than using a branch, but oh. Fingers. Hit the right keys, please. Oh, hi, NTT. Sorry, I kind of spaced out. How are you doing today? Sorry, I got a bit into too much math. Oh, it's all right. I need to... Yeah, the music service I use, they make me put these song messages in chat, but it makes it so sometimes I miss chat messages from actual people. So I don't know, I might look into finding something different. And yeah, just today they announced they've like reduced the number of songs available, but okay. So yeah, finally. Oh no, there's a hole right there. How come? Because these two should be 0. Okay, so I guess we need to have like a threshold so that if it's let's see here. Because let's leave this maybe. Okay. I think the problem here is that these 2 points technically aren't being deformed, but since the deformation shape is actually circular, the points in between them are being deformed a little bit. So since this one doesn't have any deformation, you get this hole in it. And that can happen basically anytime that the edges don't have the same tessellation factor, so it's kind of something you always have to think about. So how would I mean, there's a couple ways I could fix it. I could test a point in the middle. The problem there is it just kind of moves the goalposts, so that what happens if we have the same problem in the middle of those 2 points? I guess I could also add like a leeway value so that if there's a certain number of tessellation between, like we have to get to like I don't know how to explain it, but like basically a negative deformation amount before it'll start not tessellating a certain triangle. And I think that might be the best. So let's see. So I guess to do that, I just shouldn't have this maximum. Okay. So I need to change some stuff. Okay, well this already takes care of it because we set this deform length to 0. So if there's a negative deformation length, it just throws it out. I think what I should do here. Okay, so we take the maximum here as well, but what I could do. Let's see. It's a deform threshold. This will just be a float, and I guess we'll start it at, I don't know, -1. That's probably pretty high, but okay. Oh wait, no, that's right. Okay, so maybe let's pass a minimum value here. So float minimum, and then we'll set that here. I want to keep this in my clipboard so I don't have to look it up again. And then we'll pass the minimum. Wait. Okay, no, yeah, that's fine. Can simplify this down here, I just realized. If I could just use this version of it and I don't have to do the loop. I mean, yeah, I might as well. And then, so here the minimum will just be 0 because we don't want anything before that. Okay. So if I press play, and hopefully I can get that tear to come back up. Okay. And then I can, oh wait, so it's already -1. Okay, so something, oh. Okay, so I wasn't expecting that to happen. When I have it at a positive value, it starts tessellating more. But you can see that that fixes the hole. That's because basically we've tessellated the entire mesh now, which, you know, is counter to what we're trying to do here. I'm sorry if you can hear that hammering. I don't know why people decide to start hanging stuff on their wall when I'm streaming, but see here. I don't know if I still need that function, but it's fine. So what's happening? Tessellation, deform threshold. I mean, if we set everything to the minimum. I'm obviously missing something. Yeah, because it should... okay, well actually, yeah, I think I know what I've done wrong. No, because even though we're testing that minimum, yeah, we're still just seeing if the max deform length is greater than 0. So we actually need to see if it's greater than... Although, okay. I guess the problem now is... Well, maybe this will still work, but... Yeah, this max deform length will never be less than this. It'll either be greater than or just equal to it. So technically this is correct, but I am worried about like float errors, but seems like we're okay. So we don't really need to set this very large. So let me move this around and see if I can catch. Okay, there was another tear. So we need to be a little bit bigger. You just kind of gotta experiment until find the right value to catch all the holes. Okay, this one seems pretty good. Okay. So what else do I want to do? I guess we should try it with more than one sphere. Maybe set this one to have a smaller radius. Okay, so it doesn't work because the max deformers is small. So I'm just going to set it to 4 and put this to 4. Deform position exceeds previous array size. What? Oh, so it's okay, so it's not gonna let me change it unless I restart Unity? Alright, that's kind of annoying, but I guess we'll deal with it. Okay, so it does not seem to be working. But it's probably not, it might not be the shader. It could be C# script. Oh, it is the C# script because I have to add it, the new deformer here. It's not, it doesn't like automatically get them all. Okay, there we go. So it's hard. Okay, it was right. Is this the wireframe shader? I think sometimes draws through. If I turn it, well, that doesn't really look very good either, but. So we can decrease the size. Yeah, I don't like the math, like I said, because you can see even when we decrease the radius, it still like kind of starts at 5 outwards, where I really don't. I want to be able to adjust this range a little more. But yeah, I don't want to get stuck on the math, so we'll figure that out later. Can the deformer be another primitive than a sphere? Well, it could be, but yeah, the math doesn't support that right now. I'm not, this is kind of just like a proof of concept, so I'm not sure if I'll do any other types of deformers at the moment. Okay. So, I mean, okay, so we know it works with multiple deformers, so that's good. Now let's start maybe trying to get it to look okay. So the problem right now is, so we have the wireframe, but so why is it? I'm trying to figure out why it's dark at certain areas. Because I don't change the normal at all. Also, I'm just noticing it's not the tessellation. It's always fully tessellated now. What's up with that? Okay. I think it probably has to do with some of the, like they're technically being objects at 0, 0. Maybe? Because yeah, it's not deforming, but we can see when I set this threshold to 0, 0, it works correctly, but if you ever get to do water with tessellation, a deformer for the water, not to clip with a boat, would be pretty good demo. I think it's Assassin's Creed Black Flag does something like that. Oh, that would be cool. Yeah, I think yeah, we'd use a system like this for water, I would guess. Because yeah, you'd definitely want it to have more vertices at points that actually has to curve. So you'd make like a, I don't know, I'm thinking pie in the sky right now, but I'd probably make like a wave height map that all different things could draw to, and then I would tessellate it more based on like where the slope and the height map is higher. But anyway. I guess this is a pretty good starting point for that kind of project. So kind of never realized that until now. Okay, so what's the issue now? Oh yeah, so I'm going to test something. If I make 4 deformers, will the threshold thing work again? Oops, I created too many. Okay, let's clean this up actually. We can just, oh, I don't know. I was going to say we can just have the deformer manager find all of the deformers when the scene starts up, but that might not work if some are disabled, so I don't know. We'll just go like this for now. Okay, so now if I disable, well no, I don't want to disable them all, but okay, so now it works. So for some reason having, yeah, so if one ever gets disabled, the threshold doesn't work anymore. So maybe what I need to do, something is, if the radius is 0, then we need to basically return like negative infinity from this deformation length. I think that's the problem. Yeah, because if the deformer strength is 0, then this returns 0, which, yeah, this is not what I want right now. I guess the other option is we could just do a real for loop here instead of doing an unroll. I mean, I guess we can do that. We already get this deformer count, so it's a little less efficient, but I think it will make these, or this system, work a little bit more intuitively. Okay, So yeah, just instead of looping through every possible deformer, even ones that don't exist, we'll just loop through the ones that we know that C# has told us are active. Okay, kind of made a mess of this. Okay. So now if I turn that off, okay, it still doesn't show up, but we it doesn't mess up the thresholds. Okay. How that happened? Okay, so now I guess we just need to make this kind of pretty. We can work more on the math. Okay, so pretty much this works good, except I want to be able to... Oh, I know what we should work on actually, the normal vector. Yeah, because it doesn't update at all, which is kind of a problem for lighting, obviously. I don't want to spend too long on it because this is, again, just kind of a proof of concept thing. So let's see if we can find an easy way to get the normal vector to work. So let's just return float 4, input normal. So we'll just output the normal vector so we can visualize what's going on. Okay, so I guess it's negative right now. So I guess I'll just invert it so we can kind of see what's going on. Okay, so yeah, it's magenta right now. Fine. I mean, I guess I could make both visible if I half this and then add 1. I guess it's a little safer for now. Or add 1/2. Okay, this is a little harder to read what this distance actually is, but basically I just wanted to change with the deformation. Okay, so again, we don't really know the deformation values for what am I trying to say? We don't know the deformation values for each point, like the points that are adjacent to this one. We only know them for the triangle that originally was this patch. So we could take that and then generate a normal from that triangle. We could also figure out, yeah, we could also just deform positions, like nudge this to the bitangent and tangent vector and then figure out how much they're deformed and take the cross product, kind of like we did in the foliage shader. Maybe we'll just go with that. Okay, so that means I need to get the tangent vector. I guess we might as well. Okay, and okay, so yeah, we don't need that any farther in the shader. Okay, so now I can pass in the tangent vector here, and it will also convert that to world space. But kind of, I don't know, I guess it's a little annoying. They don't include the bitangent bit. So you have to add that in like this. Oops, .w. Or it's not a bit, the flip direction, but okay, so then so now we need to calculate the normal vector. So float 3. I need to get the bitangent. So bitangent world space equals cross product of the normal and the tangent. Let's do. I'm going to be using the tangent vector quite a bit, so. Oh, we also need to do barycentric interpolation here, which is just a way to interpolate over a triangle. I think it's this interpolate. Okay. I need to normalize this. Okay, and technically we're supposed to multiply the tangent W bit here, but it doesn't really matter at this point. That's only to make sure the bitangent points along the V axis of the UVs, but we're not actually working with the normal map right now, so it's okay. So I guess I didn't need to pass along the bitangent flip variable, but it doesn't really matter. Okay, so float 3. This will be position nudge tangent. Okay, so we basically just call this again. So it's position world space plus this. Okay, actually no, wait. Okay, let's define normal reconstruction length. Again, I don't need an equal sign there. Okay, and then we can just use the same thing for the bitangent. Okay, and then these variables get kind of long, but so deformed position nudged tangent. I think I'll just shorten it a little bit. Is the position nudge tangent plus this. Okay, and then we do the same thing for the bitangent. Okay, so I hope I've got this math right. And then what we need to do. Oh wait. Yeah, I also have to multiply this by the deform direction. Okay, so now we take the. We don't really need a new tangent vector, so I don't have to do that. But so the new normal vector is cross product. Okay, I might get these flipped, but okay, so yeah, you take the position. I think it's this minus position. I just did this in my video, but I've slept since then, so I don't remember it exactly. Okay, and then I gotta normalize that. Okay, so yeah, we're basically constructing two vectors here. So, well, basically we have a tangent and a bitangent, and we're kind of like reconstructing a deformed like normal space here by deforming these positions and then reconstructing a new tangent and bitangent vector and then taking the cross product to get the normal vector. Another way we could do it is just say that the more it's deformed, we point towards the deformation object, but I don't know, that probably wouldn't be quite as good quality. Okay, expecting some bugs. Oh yeah, so I don't have to include that there because it just reads from the patches. Okay, so something's happening. Not sure what's up with this ring. Okay, let's just hide these three so we can work with one at a time. Oh, yeah, it's not going to do anything if it's not play mode. Okay, so I'm trying to figure out why is it... What does this mean? Okay, it's hard for me to read the normals when it's like this, so I think let's go back to just doing the negative normal vector. I guess we could just do the positive and see. Okay, so this is saying the normal is pointing in the x direction, which is not right. I think what I'll do, let's just have this face directly towards the camera to make things a little easier. So that way they'll be aligned. Okay, so that's actually right. So this x, so where red shows up, it's pointing in the x direction, but obviously that's not right because the normal should not be pointing in the x direction on this side. Let's see. So these areas are right because they're pointing, well, the negative normal is pointing in the z direction. I don't want to do negative because I know it's gonna confuse me. So if we look on the other side, oh, it's invisible. Okay. All right. So green, that means it's pointing down, so that's not right. Okay, so obviously something's wrong, but kind of working. Do I need to... Okay, well, let's just pull up my code from my foliage shader. Why not? Maybe we can show what's going on. Okay, no, that's probably not up to date. Where is it? I thought I had... Oh, it's the research, yeah. I was gonna say, I thought I had a file that was just for the wind stuff. Okay. Is this... Yeah, I thought I had this stuff. Oh, it's in a different folder. Okay. There we go. Okay, so deformed position. So it deforms the position, which we've done, and then nudges by the tangent and the bitangent, which we've done. And then, okay. So add the nudge to the, oh, okay. Did I do that? So you're supposed to add it to the, oh, okay. I don't know why that had to do it during my stream. Thank you very much, Pretzel. Okay, so yeah, so I'm adding this to the deformed position when I actually want to add it to the original position. Okay, so I guess we can just copy the original position. Where is it? Undeformed position, world space, and then we'll just get the real position world space here. Let's see. Fortunately, didn't really seem to fix the problem, but it does look a little different. Okay. Oh well, I'm still using the deformed positions there. Okay, and then here for the cross product. Okay, so get that minus the deformed position, and then okay, so I think this is right. Oh, there we go. Okay, so this is negative, so I think this is correct because the reddish parts are pointing in the negative x direction, and then the greenish parts are pointing in the negative y direction. Okay. So it's funny, just that one little tweak. All right, so if I turn this off. Okay, we still got these funny, is that a shadow? It might be self-shadowing. So if I just turn off cast shadows, okay, that does look better. How would we get shadows to work though? Do I even really care? Well, technically it's already using this stuff, so I think it's just because, I don't know, I mean, shadows are always kind of a pain. Oh yeah, so I just need to turn on two-sided shadows, I think. Yeah, because so basically what was happening was when I had on single-sided shadows, this was just being deformed so much that the light wasn't casting shadows from this back side of the mesh, which is invisible. But if you turn on two-sided, then it turns off culling for shadows. So, okay, so that was a relatively simple fix. Okay, so what? There's these little creases there. Is that? I think that's due. It kind of looks ugly, but it's due to. Also, there's bad culling there, but it's just because we have such a sharp change in normal there that it's the interpolator for the normals is not the best. So is there some way that I could get this to do normals per fragment? I guess technically we could do this per fragment. That would look a lot better. Do I really? I mean, this does kind of look bad, doesn't it? But I mean, it's mostly just because of the triangles themselves. So in order to fix that, you would want more tessellation. So maybe I'll leave it just to kind of show. So if you wanted more tessellation, you could increase. I'm just gonna turn this up. You could increase the bias, but it's always a little bit because okay, that's a lot of tessellation, but you're always going to have a little bit because your tessellated vertices aren't going to match up exactly with the drop and the height map of whatever you're working with. Okay, so what else do I want to do? I guess I still need to do the math to make this look a little better. I mean, it looks fine. It doesn't really work how I want it. I guess, I don't know. Like I said, this is mostly a proof of concept, so I don't really have to get it perfect. Let's see, let's make the lighting a little better. In fact, I kind of liked can I copy? Yeah, I wonder if it'll let me paste it. Well, I liked the colors better on here, but it's actually kind of messed up what I had it set up before. Let's see. Okay, so I guess I could just, if I want to be able to see this a little better, or you can have the lighting minimum, although. Okay. Oh, I think this fade range is what's confusing it. So I really don't want it to fade, so I'm just going to set it to a really high number. Okay. Yeah, that looks better. And then I'll set this to just be constant again. Okay, there we go. Yeah, no, don't need smoothing mode for this. Okay. Let's move. Let's do. I guess what do I want the rest of this to look like? I think I'll move over a lot of this stuff and just reuse it. I guess I don't really have to copy the model. So this will be the floor, skybox, and then the deformer is going to just use this. I don't know if I want him to have the wireframe, but something like that is fine for now. And then bring out, let's just open this up. this to be situated. Why does that mess up the shadow caster? Oh, I forgot to turn back on two-sided. Let's see. Okay, that looks pretty good. The floor doesn't really need to be tessellated, but it'll be fine. Okay. Oh, I was gonna say, yeah, the shadow looks funny, but that's just because we're kind of moving to the outside of the deformable wall. Okay, I think that does show off the system pretty well. So what I want to do, okay, so I guess let's finish off the stream by refining the math a little bit. Is this? I feel like the shadow. Is this supposed to be like that? Where is the light pointing? Okay, I guess it's just the shadow looks funny when the way that it's set up, but I think that is actually correct. I guess it's this little cutoff that's making the funny shape. Yeah, because it goes away when that does, so. Okay. All right, so let's. I mean, I can always. Again, if I want this to be like the radius that it starts, so maybe I can do something like that. Okay, so then it would be similar, sort of. That. Okay, I mean, that looks fine. Okay, so then if I wanted it to increase when the ball goes deeper into the wall, that would just be. So again, we would just do something with a dot product. Okay, let's bring this back. Okay, so if the dot product is less than 0, then that should be what we've done here. So we'll just return this. Otherwise, we'll just return 0 and see how that looks. I don't need this one anymore. Okay, so no, that's not right. What is going on? I just feel like it never works how I expect. So the moment I pass the plane, then it starts to deform. But now it's saying that it wants to deform the entire. Oh, that's because we set it to 0. I need to set it to the minimum. Or like negative infinity. Yeah, so if I. So that probably won't happen anymore if I do something like that. I hope, anyway. Okay, now this is really confusing me because it's deforming at this point, but it doesn't tessellate. Oh, that's because I forgot to send the negative normal. So technically, yeah, those functions weren't using the same movement direction. I'm surprised that didn't cause an issue earlier. Okay, so that works. But I guess I did get the sign wrong with the dot product. Okay, no, this is right. This is right. Okay, so I think what's confusing me is because this difference points from the deformer to the vertex, which is kind of opposite of the movement direction. Or wait, no. I'm not going to mess with it. It's just too much for my mind at the moment. Okay, so if this is true, then it's 1, or wait. So if the distance to the deformer is 0, then it starts at a deformer strength. So basically what we'll do is just add... Press the wrong button there. Hope that doesn't slow down things too much. There it is. I'm leaving those parentheses because I want to add like a scaling amount. Okay. Okay, so what's happening here is, yeah, the points that are farther from it are getting deformed more. But what I actually want to happen... Maybe what I want to do isn't super easy, because kind of what I want to happen is the farther the deformer, or the center of the deformer, is from like the closest point on the plane, the deform strength will go up. But I don't... So yeah, when I move past it, it can't actually be based on the vertex position, because then it's not continuous, as we see. So the only point here that's continuous is actually the point that's closest to the sphere on the original plane. Okay, so you could do a point plane distance pretty easily, I think. Right, so distance from point to plane. I think it's just like projecting and stuff, so... Okay, so the distance is... Okay, so in this notation, the normal vector is this A, B, and C. Oh yeah. Projecting W onto V gives the distance D. Okay. So yeah, we just would take... Okay, well, that's kind of what we're already doing, because so we project the... Is it really just this? So maybe what I do is just add the negative deform dot. Well, this is gonna makes it like depend. Well, I guess maybe it does. I was gonna say it makes it depend not at all on the vertex position, so I don't know. It's gonna make it flat. Not exactly, but it doesn't work either. Okay, so projecting W. So W is the vector from the plane to the point. Okay, from any point. So we project this onto the normal vector. And again, projection is, so A onto U, so it's A dot U over the length of U times U. So the length of the projection is this A dot U over, okay, so that is a little different. So it's A, okay, so, okay, but again, if the normal vector is 1, then it's just a dot product. So that's kind of what we're doing here, except this is just the direction and not the, okay, so let's do this. So float, project to plane is a dot product of the difference and the movement direction. So technically this deformed dot product then is this divided by the distance. Okay, so let's just make sure this works so far. Okay. Then maybe if we use this here. Okay, no, it just makes it, like I said, it's just, it kind of works because we can see that the more we move, the more the points move, but they're not, it's constant. So basically we want it to continue deforming as it moves through the plane. This is a bit more complicated than I thought. Because basically we just want to add, let's see, can we figure out, like if this is 0, then we just add this onto it. So if this is 0, then what would happen? So that would mean that this is 0, which basically only happens when the difference is 0. Okay, so this would be relatively easy to do in C# because we can do everything at once. So all we'd have to do is calculate the distance to the closest vertex, and then we would just kind of deform each proportionally. But since the shader only knows of 1 point at a time, I'm having trouble wrapping my brain around it. Let's see. Maybe what I do, okay, so what happens like if I just ignore this? I think we kind of did this already, but I'm just curious. So, oh yeah, so then it just kind of does like an absolute value type thing. because the distance to the deformer starts growing again. What can I just like multiply by the deform dot? No. Yeah, that's because we don't deal with negatives very well, do we? Yeah, I know I'm doing double negative there, which is like kind of okay, so that doesn't work either. Because basically I just want this distance to keep growing as you move through it. Well, no, that is what happens actually. The problem, again, it's like clamping at 0 that messes us up. That just makes the whole thing go. Okay, well, I don't know. This is starting to... This is going to bother me. I feel like this problem isn't as difficult as my brain is making it at the moment. Okay. What about... what does it really... It's not much different. I was going to say, what if we use... project to plane, and then we use either positive... Oh no, I guess the distance to the deformer doesn't. Sorry, I'm trying to figure out things out in my head and talk at the same time. Okay, so again, so I guess if we take like this, if we make a function over the distance to the deformer, so if it's at a positive value, then we want to subtract that from the deformer strength. So that works fine. And then at 0, we want it to be exactly this deformer strength. But then after that, we want it to kind of keep growing linearly. So I feel like this shouldn't be so difficult. Deform dot should tell us what side it is. Okay. Oh, but yeah, the issue is, yeah, it doesn't work for vertices that are not closest to the deformer. So yeah, so that's a difficult problem. I guess I could, instead of, I guess that we could do the whole thing by finding the distance to the center and then offset these side ones just based on the distance, like that they are from the closest point on the plane. Maybe that's the better way to do it. Okay, so we have this project to plane, so then the point on the plane, equals this okay, so it'd be the deformer position world space plus project to plane. Yeah, and these variables are all not greatly named, but we'll figure that out. Times the deform direction? No, the movement direction. So then, okay. Flipped deform. Okay, this is, I need to clean this up, but so instead of using this, we'll just actually use this project to plane for both. Okay, and then the actual deform strength will be this. We'll just take like the distance of this to this point on the plane. So will we return distance, vertex position, point on plane, and then divided by the strength. Okay, well, strength can be. Okay, I guess we'll just do subtracted by the strength. Yeah, so that way it'll be linear. Okay, well, kind of works. Because at least when we pass through here, it keeps growing, but it also happens on the other side, so. Maybe, okay, let's see here. Maybe I just do this way, both sides. No. Maybe it's something like. No, that doesn't work. Okay, so this is basically right, except it's inverted. Well, the whole thing is inverted, isn't it? Because it shouldn't be stronger the farther it is. So maybe this is part. This has to be. So when this is 0, the distance should be greatest, actually. So how do I deal with that? Oh, maybe I just do this opposite. So strength minus the distance. Okay, well, no, that's wrong, but it's inverted, so kind of getting there. Something like this. It seems like the deform dot doesn't matter anymore. I think I might be on the right track. Oh, there we go, finally. Okay, so now it's kind of a cone. That's fine. If I wanted to make it like more of a parabola, which I think is a bit more natural, what would I do? I guess I would just maybe rise this, multiply the strength with itself. Okay. It's nice I don't have to worry about that deform dot anymore. Okay, so let's see. So strength equals, I guess it multiplied by itself. Let's see how that looks. So hopefully it'll be a parabola now. Oh yeah, I have to press play. No, I've messed everything up. Oh, right, because now I've made it unsigned again. Okay. So I guess technically we could do like a cube. So strength equals strength times strength. And then I'm just going to multiply by some small number because it's going to be really big otherwise. Let's see how that looks. No, it makes it like, okay. I don't know. I think I might just be happy with having it as a cone. Probably, actually, what you might do is instead of doing stuff with the strength, you would do something with this value. Like, let's just try that one real quick. Okay, so return. Okay, well, it works, but it's like kind of the opposite of what I wanted. I wanted it to be a little bit smoother and not have as much of a point. So, okay, I was gonna say we would do the squared root or the cube root. Okay, yeah. Well, nobody said this was going to be efficient. So, okay, that works, but it's a little bit too strong. Let's see. Now, if we do a square root, it's gonna, because you can't take square root of a negative number. So I think it will, I guess it still works. I'm kind of surprised. But the problem is it doesn't really follow the distance anymore. So it doesn't really work very well. Okay, so I guess we'll stick with a cone. It's fine. There's other mathematical things, but you can see how you can use tessellation to kind of visualize equations on a mesh. I actually did something sort of similar on another test scene I was playing with, which I guess I'll show in a second. But let's okay, there we go. I was gonna say, why does it not work anymore? I'm just making sure that having multiple versions, basically all it does is take the biggest distance field. So yeah, actually with this we've kind of made an SDF, so you could basically just create any kind of SDF shape you wanted with this system. It's probably not as I think that ray marching is more efficient, but if you ever had to do it with tessellation, you can do it this way. But anyway, kind of cool. Okay, let's see. Okay, so now I guess how do I want to make this into a final thing? Is there no fix to the jagged edges? Well, it's just kind of a, you know, you could continue tessellating it, but at some point, that's I guess, the downside of tessellation. Let's see, 'cause I can increase the bias here. And as you tessellate it more, it gets better, but basically you're creating a vertex. We could kind of fix it if I calculated normals per fragment, which I guess we can try and see how that looks. We won't really be, you know, actually creating geometry, but it will look smoother. Let's see. To do that, I just need to call this function in the fragment. So okay, that means I need to pass the tangent vector through here. Oh, this should be a text port 2. And then we'll pass the output dot tangent vector. Okay. And then I just got to pass the tangent vector through here. So not really. We basically only use a geometry function for the wireframe effect. All right. So can I extract this code somewhere cleaner so I can reuse it easier? So float 3, generate normal. Okay, we'll see what we need. So I guess we've got to pass the flat normal and the tangent vector. Okay. And then we would return this. Is that right? I guess it needs the original. Okay. So we're going to need the original position as well as the deformed position. So we're going to have to pass the original position through, which is not a huge deal, I guess. So let's see here. Flat position. I guess alternatively, we could calculate the new world position again instead of having to interpolate it twice. I don't really know if that solves much. Except we could put all this in one function, I guess. Trying to think. So if I wanted to turn back on, if I want to toggle this on and off, what would be the easiest way to do that? I guess the easiest way would be just to pass the position through. So technically this is a little less efficient, but I mean, we're already using a geometry and a tessellation function, so this shader is not the most efficient. Okay, so we have the float, flat position, and deformed position, the flat normal tangent, and then we just return the new normal vector. I guess we can bring this out just to make it a little cleaner. Okay, so and deformed position. Oh, we need this deform direction. Well, I guess we kind of know it's just the negative normal. Oh. I feel like this is going to be a little hacky, but okay. Okay. Let's just. I just want to test how this works. Yeah, we need to. This is not good coding practices. Okay, so flat. Oh wait, no, this is the deformed version. Okay. So then can I... You know what, I'm just going to leave that how it is for now, in case I mess something up. Okay, so let's make a toggle here. Toggle. Calculate normal and fragment. Wait. Yeah. Set that to 0. And then we need to add a shader feature for this. No, the shadow caster doesn't need it. Okay, so if we calculate the normal and fragment, then we'll basically I guess we'll just kind of ignore the normal that was passed through. So when do I use the normal vector? It's just here. Yeah, this is very messy. 3 normal world space equals input dot. Then we'll call this function. Yeah, I gotta delete that because it's gonna say it was defined twice. Okay, so I need the undefined or undeformed position. I can't remember what I called it. Flat position. That should just be it. Oh yeah, and I also need to pass that through here. Put flat position world space equals. Again, I'm using different names here. Trying to finish this up before the end of the stream, so I apologize for the messy coding. Position world space. Yeah, I guess I do need the regular normal. And then the tangent world space. Okay, so this normal is going to kind of be deformed twice because I guess I just need to turn off the recalculation when this is on. So if def or if not defined, we'll do this. Okay, so let's see how many errors that gives me. Oh, it keeps on giving me this. I fixed that. Deform direction world space. Oh, okay. So yeah, we're just gonna say we deform in the negative normal, which is true, but I don't really like doing that here because it's kind of redefining that value. But so no bugs now. So if I turn on Calculate normal and fragment. Okay, we get something. Undeclared tangent. Oh, because the tangent world space. Technically, we don't really need that always, but okay. Let's hide a bunch of these spheres. What's up with the tessellation? Oh, it has a tessellation bias. I was trying to figure out why it was adding to it. Okay. Okay. The normal's messed up because I can tell there's no specular highlight. Let's go back to just outputting the normal. See if we can figure out what's going on. Why is it? Okay, so purple. Purple means. Okay, well, it's all the same color, which is not right. What would be? Turn this off. Okay, so purple is just what? Oh, because we're not. Okay, I was confused why this wasn't blue, but it's just because we're not, you know, aligned with an axis. It's fine. Okay, so something is not calculating it right. You're tessellating more by distance or by the angle of deformation. It just only tessellates by the amount that it's deformed. And right now it's basically on or off. It doesn't like it doesn't tessellate more based on the value, and that's because we were getting like holes in between the vertices if you varied it too much. Okay, so what? Generate normal. I feel like. Okay, let's just make sure that all these values were passed correctly. Oh, looks really funny with the bloom. Okay, well, we know positions, right? Because it worked before. Oh, you know what? I was using the input normal and not the normal that was recalculated, so. Okay. Well, we've got something. Maybe they're. Okay, no, yeah, I'm not using negative, so X. Okay, let's make this axis aligned so I can tell what's going on. Did I fix that normal but problem I was thinking of? Because I can see the. So is this doing smooth normals? But you can see, I can kind of see the tessellation pattern. But I mean, it is. Well, I feel like it should be higher quality. Wait. And then I need to change the. Oh yeah, I think this was the reason why the lighting wasn't being updated. I need to change this to use that new calculate normal instead of the one that was passed. Okay. kind of surprised that didn't seem to help. Well, I guess it does a little bit. There's still... Okay, well, let's turn it on and off and see the difference. What's going on there? I guess I'll turn off shadows. This is... Oh, you know what? I think that's the point where the cone... I think that's a rim light. Yeah. It does look a little smoother, huh? It also highlights these crisp edges. Let me turn back on the normal color mode and just see what this looks like as we toggle back and forth. Okay, so I don't really know why it's saying this part is green, because that's the only thing that's a little strange. Actually, yeah, this kind of has a weird pattern. It's not a sphere. Why is it making a cone shape? Well, no, I'm not really deforming based on the object. It's just kind of just a visual representation. It doesn't actually use colliders or anything. It basically just finds the point closest to the sphere and deforms based on that. Or the point from this object closest to the plane. Yeah, I don't know. Yeah, okay, something's still wrong, obviously. It probably is because I've missed some bug somewhere, because I kind of did this kind of quickly. But let me see. Oh gosh, I only have a few more minutes, but let's see. Just calculate deformations. So here we'll just return, or have the original. And then I'll output deformed. Okay. Yes, we'll be able to see a little bit more what's going on if we use the same code for both instances here. Okay, so yeah, this should return nothing now. Okay, so what else? This flat normal I've changed to original normal. Flat position. Oops. Change to... Oh. If we're going to type it out. Okay, so now we can delete this function. And all right, so now here. I'm just going to delete, well, I guess not all of it, but oh yeah, I forgot I have this macro that I can just calculate the tangent and normal at the same time. Three. Okay. So now I'll call this new function I just created. So it's a normal position, our original position, normal and tangent, and then the deformed versions. Let's use the same naming here. Okay. I don't need that stuff. So calculate deformations. Okay. And then we'll have the deformed. Oh, I guess we'll just have the final positions. Okay, and then we can output that. The only thing is, we don't want to output a deformed normal if we're calculating the normal in the fragment function, because that, I guess we also don't want to output the deformed world space now. So we still need to calculate this because we need the deformed position for the clip space. Okay. Okay, so I guess I don't need this flat position anymore, which I kind of didn't like adding it in the first place, so. Okay, so now we can get rid of this. And then to calculate, if we calculate the normal and fragment, then I just need to call this calculate deformations functions. Oh, I don't know the deform length anymore here. I guess that's okay. If I need it, like if we have to debug again, I can just output it again. It's still going to be a foot 4. But I think I could just switch it back to a foot 3. Yeah, I still need to pass the tangent. And then the original position is actually this now. And we don't have the tangent yet, so input tangent XYZ. I think this will work. It might complain that I'm recasting it, or like setting this and the out version. We'll see. Valid subscript. Okay, I think I messed up my macro. Yes, the patch factors, smoothing the normal and the tangent. Oh. How do I fix that? I guess I could just do that because basically I just want to save the values in this. I need to keep that in mind when doing macros. Oh, I've left one of them as a float 3 probably. Or float 4, I mean. Okay. Oh, that looks much smoother. So yeah, I did have a silly bug somewhere. Yeah, that's a lot better. Okay, that makes a big difference actually. Okay, so let's turn back on the lighting. I guess another cool thing is that we're calculating the position per fragment, so we don't have, so that would also improves the smoothness. Okay, yeah, that looks better for sure. Let me get a better view. Okay, there's still a kind of funny bit right there, but I think it's the rim lighting. Oh no, it's the shadows. So I just need to turn two-sided shadows back on. There's still, I guess it's not completely the shadows. Yeah, it's much smoother now. Yeah, I don't know what bug I made, but it looks a lot better. Let's see. Yeah, look at that. That makes a big difference. And we haven't actually changed the geometry. It's just that we calculate the normal per fragment. There's this little bit, but I think that's, like I said, it's just flat at that section. So I don't know. I don't know if I'll worry about it too much. Let's see. So add in more. So this one is smaller here. I wanted to. Still looks pretty big, but it's, I guess it's because it's burrowed in deep into the wall. Yeah, it'd be cool, like you said, if I could actually make this, you know, tessellate based on an actual sphere shape. And definitely if I ever turn this into like a water shader, I'd do that for sure. But I don't know. This is kind of a proof of concept about how you can do something like this with tessellation shaders. And I think it turned out pretty well. But anyway, I think with that, it's a pretty good point to stop, and I've actually gone like 20 minutes over, so I guess I'll go ahead and sign off for today. But thanks everybody for coming by and watching. I appreciate it. And thank you NTT for chatting. It's always nice to have somebody to talk to. But if any of you enjoyed the stream, I'll put some links in the chat, and you can connect with me on other social media. I also, of course, have my YouTube channel where I upload game development tutorials. Pretty soon I'm going to make a video about everything I've learned about tessellation shaders doing all this stuff. So yeah, you'll see the fruits of my labor. But yeah, I'll be back on Wednesday at the same time, about 2:15 Eastern. And yeah, now our daylight savings time just ended, so might be a little different for everybody. So be sure to check your clocks. Yeah. All right. Thanks, NTT, and you have a good night too. But yeah, I'll see everybody on Wednesday, and hope you have a great time until then. Bye-bye.